Hello. So thank you very much for inviting me for a talk as an organizer of the conference. Thank you, Hiromasa. Um, it's a nice crowd of people that love neuroanatomy, so I thought I'll provocatively call my talk Mapping Functions on the White Matter, which usually a lot of people are very upset about. I took the occasion also to promote our journal, Brain Structure and Function. If you don't know about it, it's a journal that really dedicate a lot of its work to publishing papers that are onto the structure, the anatomical structure of the brain and its relationship to function. And we do love those papers, and every month we take great care of highlighting the illustration of one of those papers on the cover of the journal. So if you submit and you do nice illustrations, you might have a chance to end up on the cover of the journal. So, all right, I have to switch. There you go. Well, so I'll start with the beginning. You know, when we do science, we rely on observations to elaborate theories. But we can also change our observations through the use of methods. And these methods will bias and change the way we do observation, which will lead to different theory. And people approaching the brain with electron microscopy will have a different understanding from people that are approaching the brain with functional whole brain imaging. And a lot of disagreement come from that. And so if you want to study function at the behavioral level, you can't really use electron microscopy. Nowadays, you can use either the study of patients that have brain damage, typically brain lesions such as stroke, which is the most frequent one, or you can use functional neuroimaging where you put the patient inside the MRI scan, ask them to do something and look at areas that are consuming more oxygen. Since we're talking about observation, I also I'll show this video. I'm always very excited about it. Those are two neurons in a petri dish. This is an accelerated video, of course. We'll see that inside that petri dish, the only goal that these neurons will have is to connect with the other neuron. That kind of remind me when I was a young student trying to approach this famous professor in a creepy way. You'll see like what they're doing, and they connect at two different points. Those two neurons are anatomically the same. The only thing that differs those two neurons is the way they are connected together and with other neurons. And when you look at this video, you can't help but think that why are we trying always to put function on the body of neurons when what is typically characterizing their specificity is the way they connected with others? Why don't we try to put function on those connections rather than putting it onto the spatial localization of those neurons itself? It's just an idea that we try to explore with different methods. So we suggested this idea in the review with Stephanie Foucault that actually function will emerge from the interaction between neurons. And when we published this paper, we had two radically opposite reactions in the neuroscientific community. People who said, we always knew it, there is nothing new in your paper. And people who said, this is unacceptable, you cannot think that actually an axon or a connection can actually support a function. So we kept on doing research on that. And we've been able to do research on that since a long time because it was just theories that was coming from our research, thanks to a method which is called diffusion MRI. That was very well explained by Ariel yesterday, so I'll go pretty quick with this. If you take the brain, you magnify a voxel inside the gray matter, which will be the light voxel on the left, and you measure with the MRI scan the orientation of the diffusion of water molecule inside that tissue. You'll see those water molecules diffusing aleatorily, and you can summarize this signal mathematically using the tensor as a sphere, which indicates there is no preferential direction of the diffusion of water molecule inside that tissue. On the darker squares that you can see, you are inside the white matter, where you have densely packed axons that are usually surrounded by myelin, which doesn't let water go through. And this will constrain the diffusion of water molecule inside those axons and sometimes also in between those axons. And if you use the same MRI scan measuring the direction of the diffusion of water molecule and you summarize it with the same mathematical model, you'll have a cigar elongated in the main direction of the diffusion of water molecules inside that tissue. Then the idea is simple. You piece together those cigars to build trajectories that become bundles in 3 dimensions and give you at the whole brain level what we call the macroconnectome. This macroconnectome shows features that we know about the white matter. You have like the spinal cord, the arcuate fasciculus. You can have a snapshot at the corpus callosum in the middle, but it also gave like mistakes, typically such as a direct connection between the left and the right cerebellum. And this is just because the macroconnectome has a resolution of 1 by 1 by 1 millimeter at best, and axons are between less than a micron to 5 micron thick. So we're very underpowered to solve complex configurations. Now that we had this method, we were like, great, let's study patients with brain lesions and scan them with a super sequence that takes like 30 minutes to 1 hour. And the radiologists say, no, we can't do that. Don't have enough time on the machine. And then you said, well, but that's fine. I have a research MRI where I can pass my patients as well. But this is also really expensive. You'll never get like big numbers. Unlike patients don't want to stay that long in the MRI scan. So with Chris Foulon, who was here today, we developed an indirect method to assess the disconnections that were induced by brain lesions. It's rather simple. You take the lesion of the patient in the stereotaxic space, project it in healthy controls, and display the track that would have been interrupted in those LC controls, and then produce probability map of how many controls were showing this track interrupted. That's it. And then you run statistics on that eventually. So as a proof of concept, we thought like we'll start, with famous patients. So you may know. Who knows who's the person on the left? Gage, exactly. Gage is very famous because he had this large bar going through his skull, going under the cheekbone, popping out the eye, coming out on the top of the head, damaging the orbitofrontal cortex, as well as the dorsolateral cortex because it had to come out some way, and had a radical change of personality that is typically associated with damage of the medial orbitofrontal cortex in neuropsychological and neurological books. In the middle, sorry, we don't have a picture of that fellow, and we can only have his brain. You have the case of Le Boyne, which is a typical patient that had a lesion in the posterior part of the inferior frontal gyrus, typically associated with a production aphasia, and that is named the Broca area. And then on the right, who knows that fellow? That's HM, exactly, who had a radical surgery of the medial temporal lobe, bilateral, that damaged the anterior portion of the hippocampus, the entorhinal cortex, as well as the amygdala bilaterally, which is the typical case that led us to think that the hippocampus is very important for memory, because those other areas that were damaged in Phineas Gage, in HM, apparently had no importance. Well, if you apply the method that I just showed to you and try to look at the disconnection in those patients, you may have a different history of the origin of the symptoms. In the case of Phineas Gage, the bar not only damaged the orbitofrontal cortex and came out at the dorsolateral cortex, but also interrupted the uncinate fasciculus as well as frontal connections, really like the uncinate fasciculus because it will disconnect the orbitofrontal cortex from the amygdala explaining the way Phineas Gage could have those outbursts of emotions because the frontal cortex was not controlling anymore the emotional impulse of the amygdala. And the disconnection within the frontal lobe is interesting as well, because if you follow the history of Phineas Gage, he had also a planning deficit after his accident. He was coming out of the office of the doctor in thin boots and pajama pants, where he was like freezing outside and almost died, just because he didn't plan that going outside will require to wear something warm. At that time, neuropsychology did not exist, so this is the best description that we have actually in the original papers of Harlow that you can find for free, accessible online. The case of Le Boyne, actually, if you just look at the MRI scan of Le Boyne, you can see that the lesion was not only superficial, but extended to the perisylvian white matter, damaging an entire system of connections. Stephanie Fockel knows very well, dedicated to the production of language, but also a little bit of its comprehension. And in the case of HM, the bilateral lesion did not only damage the entire portion of the hippocampus, it disconnected the cingulum, the uncinate fasciculus, and the fornix. This is an interesting case because those three tracks have been associated with memory impairment, episodic memory impairment, which was the main problem in HM. The fornix, when a neurosurgeon is removing a cyst at this level, sometimes accidentally they damage the fornix, and patients come out with big memory deficits. The uncinate fasciculus, when it's disconnected in monkeys, lead to difficulties to create memories associated to emotional events. I don't know how your memory works, but mine is very much related to emotion and emotional events. It's actually a trick to remember things. If you want to remember an event you imagine and you associate it with something that will produce an emotion for you, such as your professor naked next to that thing. And then the cingulum over there, so it's also an interesting case because it connects the hippocampus with the retrosplenial cortex over here, which is a typical core that shows reduced cortical thickness, higher hypometabolism, and higher level of amyloid plaques in Alzheimer's disease, which is characterized by this episodic memory impairment. So the point that I'm trying to do is, on one hand, you can look at the localization of the lesion. On the other, you can look at the network that is interrupted. I just want us to agree that in terms of interpretation of the symptoms, looking at the connection is at least as good as looking at the localization of the lesion. We all agree with that? Okay. So let's bring it to other type of symptoms and bring it to the group level. I like these studies that we did with Valentina Pasela. It's about the link between the mind and the body. Sometimes patients lose this link. It's called anosognosia for hemiplegia. They're not able to move anymore their arm, but they're under the belief that they're still able to move. You have an example here with this video where you see this patient, Giuseppe, how is it going with your movement? Can you move your arm? He says more or less. Can you move both your left and right arms? I said, do you mean that I can move the right arm but not the left one? A bit less. Can you show me? Did you move it? Yes, I did. Did you move it? Yeah, I did. Can you raise your hand? Did you raise it? Yes, I did raise my hand. The complete disconnection between the way this person thinks his body is moving and actually how he can move it. So we tried to look at this in a large population of patients that were displaying this anosognosia for hemiplegia versus patients that had a motor impairment but no anosognosia for hemiplegia. If you look at the localization of the typical lesion, you'll see that, of course, you involve some gray matter area, such as the putamen and the insula, a little bit of the temporal pole. But the core of the lesion is very much located in the white matter. And if you use the method that I showed to you, you start extracting a network of connections that, when they are disconnected, are significantly associated with those symptoms. And so we played around and we showed off a little bit with Bayesian statistics that show you how much the damage to different areas can explain the symptoms. And you see that the insula, the temporal pole, and the putamen have a significant but small impact on the occurrence of the symptoms. And if you took those three regions together, you start having a better explanation of the symptoms. But this is nothing in comparison to the study of the disconnection of white matter tracts that explain way more of the occurrence of anosognosia for hemiplegia, with a top significance for CSLF3. Now, if you were to compare those three regions of gray matter with a region of white matter, you'll see that you have an even better model. And of course, if you put everything together, you explain even more. But the question we had is like, is that because you can have anosognosia for hemiplegia for any of those kind of lesion or disconnection? Or do you need to have all this together to have the occurrence of the symptoms? So we created this four-dimensional space that we flattened. And that was really the beginning of the entire part of creating those spaces that I'm going to talk to you about right after, to realize that actually most occurrence of the symptoms were happening where you had this group of disconnections in the brain. And the flavor of the symptom, anosognosia for hemiplegia, only occurs when you have the combined disconnection of the cingulum, the frontalis tract, frontostriatal tract, and superior longineural fasciculus 3. It can only happen if you have a lesion over there. So it's a hub crossing of connections over there. So this is interesting, this space and this pattern of connections. Can we have that a little more? Can we create a map where we put like hundreds, thousands of patients with a disconnection like this, so all the data organized together so that patients that are the same disconnection are close together, the ones that are different are far apart, and create cluster and start coloring them according to the symptoms we can find. So we can find the valley of hemiplegia and the mountain of visual neglect over there, the river of aphasia, and so on and so forth. Now, this is not possible thanks to new embedding technologies that maximize the amount of variance you can have in a smaller number of dimensions than principal component analysis. You have an example here where we embedded 1,333 map of disconnection of patients with stroke inside a two-dimensional space where you can see that you have different clusters on patients that are close together, have the same profile of disconnection. Patients that are far apart have different profile of disconnection. And then we run statistics on it with now a software that we're polishing up, which is called Emuses. You have a poster about this, and that is led by Chris Foulon. Those statistics tells you which part of that space is associated to a deficit to a specific kind of test. And this is thanks to the contribution of data of Maurizio Corbetta that gave us a data set of 150 patients that were studied with neuropsychology along multiple, like 82 different measures. I'll give you just 3 examples. So like, for example, motor left for grasping ended up in that cluster in space. And then you have language ended up in that cluster in space. And if you take visuospatial attention, it's interesting because you have 2 different profiles of disconnection that can lead to the same impairment in visuospatial attention. And that's because that, oh, my sleeper. And that's because you can have a deficit on the left on the right visual field in visuospatial attention. And those kind of statistics allow you to tackle a main issue in statistics, which is a way to reveal the plural origin of the same observation, which is a big statistical bummer for us. And so we repeat that for many different functions and project back onto the brain the typical disconnection that is associated to this cluster, and that allows us to do whole brain representation like this, where you project directly the test will be most likely impaired after disconnection of those white matter tracks. So how good is it to predict symptoms? Well, I forgot to mention at this point that the symptoms that we're predicting are 1 year after the lesion. So there is a huge clinical impact of being able to do so. So we created this software that allows you to upload directly the profile of disconnection of your map and predict for those 82 score, the scores that your patient will have 1 year after its lesion. We have here the example for motor function. And you see Leah, she's like uploading a disconnectome map, which is this profile of disconnection in the patient. Press and run will give you the coordinate and space, as well as a predicted score for all the motor function 1 year after the lesion. This predicted score is not perfect, but rather good. You can see here that predicted value can match the measured value, and if you do the difference between the two, you mostly have blue, which is a tiny difference. And our prediction is better than if you were looking at the localization in the lesion with the same space approach, or doing a lesion-based analysis, or doing functional connectivity, or just using the volume as the age of the patient, or just using the mean over there. Out of sample, this prediction is able to predict with an R-square of 0.2 the score in verbal fluency of patients from United States. I think it was like Ohio. And the visuospatial abilities of patients in Grenoble and in Lille in France, those are like data sets that we've never seen before, that we just put in the software. And this was significant. So the prediction online is available for free. You just go on the website and you can predict your patients. Individual prediction are also like quite interesting, although usually our tool is more optimistic for the performance of the patient than the actual observation. But you can see that, for example, for a patient with language impairment, the area where you have dent over there were also captured and represented at the individual level. So, a little interim conclusion. We've been looking at the white matter rather than the localization of lesions in patients. And it seems that it really helps to predict the symptoms of patients and explain the profile, the emergence of the symptoms they can have according to the profile of disconnection they had. It's quite satisfying to think that maybe white matter is an interesting parting shift to explore when trying to understand the functioning of the brain. Another way to study function is to use functional MRI. Although we developed also a method for that, which we call the functionectome. We're very good with names. It's like always like a mouthful. Although like it's quite simple. You do the standard processing with fMRI. You get your raw fMRI, you do pre-processing, get your pre-processed fMRI in 4 dimensions, or like several 3 dimensions together. And here you're going to apply the functionectome that will transform your volume of variation of the board signal and project it onto the onto the white matter according to the probability of connection of each voxel in the cortex with other voxel in the cortex. It's a weighted sum value. The theory behind it that we're trying to test is that the whole, the weighted sum, will be more than the sum of the part, which will be like, will have the same level of significance. So we think we'll have a better level of significance by integrating the connective property inside fMRI. So this is what we explored. For example, with finger tapping. So you do your finger tapping, and what you have with fMRI usually is this profile of activation in brain regions that seems to be wirelessly connected. But if you apply our methods of functionectome, you not only have those cortical areas, but you obtain a set of connections that we do know when they're disconnected are really important for the motor behavior, such as connection with a striatothalamic network, as well as the spinal cord and connection with the cerebellum, which will be all very important for the finger tapping behavior. So we tried to apply this to different questions, which is consciousness, visual consciousness, by using a set of paradigms and manipulate attention differently, either by using a preparation of attention or a spatial priming of attention, or an executive function priming of attention. And the task is always to detect a gabor, which sometimes is visible and sometimes is not visible, just as a threshold of vision of participants, and say whether this gabor was on the left or on the right. By doing so, you do a contrast between people who saw something versus they didn't see something at a very small level of difference in terms of visual stimulation, and independently of the attention, because you manipulate it in 3 different ways. If you do that with classical fMRI, you obtain those blobs in the intraparietal sulcus, and you get a little bit of medial frontal lobe somewhere on one of those slides that we cannot see. But if you do that with the functionectome, you gain insight into a large set of connections that are also significant. If you compare the level of significance with the classical analysis of fMRI with a functionectome and plot it as an histogram like this is a classical fMRI will give you a nice Gaussian, typically centered on 0, and we usually display this part. That is what we call the significant activation. We can also display this part, which will be significant deactivation. If you look at the functionectome, you have a rather hard distribution, whereby deactivation did not significantly load onto the white matter, like in a significant way, but activation actually showed this like boost of significance. And that makes us think that actually, this is a demonstration that being aware, being conscious of what you saw requires interaction between brain regions, better captured by our model of fMRI onto the connection than looking at individual voxel activated in the brain. So if you're interested in a consciousness, like the models that we have is to be aware of what you see, to be conscious of what you see, you'll need to project from the beginning of the ventral visual stream onto the frontoparietal network that will maintain this visual representation and allow you to manipulate it into a conscious way. But in order to verbalize it, you'll have to always use the callosal connection to connect with the left hemisphere. And the thalamus in there is like connecting all those regions to manage and monitor the synchronization between brain areas. That's actually the putative interpretation of this set of connections. Oh, sorry, that's the model. And then you can repeat that as the whole brain model with as many functions as you can have. Although you cannot have the fMRI, you cannot use the functionectome, but what you can use neurosynth and try to decode it with a pattern of connection in the brain. And then the same way, you're going to project the term from neurosynth, which is a huge meta-analysis database, onto the white matter, and here you have like the peak contribution of all those white matter portion to different functions. You see the curve, the phonics is really associated to memory, which is quite nice. And you have on the left hemisphere fluency and pseudo word that connect more like onto like this temporal area. And then you have a lot of, if I remember, inhibition that happen in the right hemisphere, which is poorly known in comparison to the left hemisphere. As you can see here, the effect size is much bigger in the left than in the right hemisphere because we don't know very well what the right hemisphere does. All right, and this is a final experiment that I'm going to show to you. We thought like, it's great, it's neuroimaging, and I do understand that people that are actually digging into real neuroanatomy might always be like kind of dubitative into what neuroimaging can show. So thanks to the European Community grant that I had, I was able to build a squirrel monkey lab. And squirrel monkeys are really interesting because you can like raise them together in the same cage. They're very nice. They play with you because they're not aggressive. They do not smell bad. Where is Thomas? Thomas, they do not smell bad. They actually smell okay. And they're not so far off in terms of evolution because the rhesus monkey, our common ancestor, is 25 million years ago. The squirrel monkey is only 35. And in terms of brain structure, they're more circumambulated than the marmoset, which allows us to better investigate the white matter organization than in the marmoset, because without circumvolution, you have less specificity of the different fasciculi. It's been quite well mapped during the second half of the 19th century in terms of functional areas. You also have all the visual areas. You have a good division of the motor cortex and the premotor cortex, although those maps are not comprehensive and do not cover the entire brain. And on the contrary of some people claiming there is no mammillary body in the squirrel monkey, there is actually a mammillary body in the squirrel monkey. And so like, we also had the chance to be able to scan the squirrel monkeys at very high resolution in Paris. We use a 11.7 Tesla Bruker scanner that allows us to have diffusion weighted imaging at 400 micron. And at 400 micron, you see cool stuff such as a macrogeric and microgeric organization of the dentate nucleus, or the separation between the external and the extreme capsule in the brain. And that allows us to do tractography of the SLF1 to 3 and test whether surgery or pharmacological inhibition of one of those tracks might, independently from touching anything in the cortex, might lead to a behavioral modification. So in terms of behavior, I decided not to put them in front of a computer, but rather build this puzzle where those rather charming monkeys have to open up the window to get a reward, and then you can play around with reinforcing or using different targets and see how they behave. Here, like the model that we're testing is whether they will equivalently explore and take the reward that are on the right and on the left of the puzzle. This is a training setup, so they're free to come and go. But for the testing setup, we actually have an entrance that forces them to be right in the front of the puzzle, so they cannot come from one side and just pick up something. So, and they're very good at that because they like the rewards. So before we actually, the day before, we actually do the injection of lysophosphatidyl alkaline type 1, LPC, which is a demyelinating injection. They're very good and they take like all the reward on the right and on the left. And then we do the injection onto the LPC injection. You can see here on the MRI scan, it's made by a robot, and we're trying really to target, you can see like the point of the different injection, really to target where the frontoparietal connections are going at this level, because we're sure we're not going to impair any motor regions, and we're trying to very finely only interrupt those connections. And what you have after the injection is a radical asymmetry in the behavior. They will only take the reward that are located in the right and not so much the one on the left. Except for G+4, I don't know what happened, but this is preliminary result. And this demonstrates that in order to be aware, conscious of your environment, you do require this interaction between the frontal and the parietal lobe, and not just a lesion or like the contribution of one of those regions. Final conclusion. So white matter does matter, and it is not trivial. We did show that actually injecting knowledge about how things are connected inside your model do explain better function. And the way it's not trivial is the way we look at the brain functioning, which some of you are already looking at it this way, but some others actually rather disagree. The way the brain functions, white matter is really important, is through an integrative mechanism and interactions where the whole of the contribution of the neurons is more than their serial contribution, which would be timely really difficult in the brain. And that represents the ideas that function emerge from the interaction between brain regions, and why we should map those functions onto the white matter and not onto brain regions. Thank you.